1946. At the Los Alamos National Laboratory, a mathematician named Stanisław Ulam, a Polish immigrant, co-inventor of the hydrogen bomb, and one of the sharpest minds of the Manhattan Project, was recovering from emergency brain surgery, left temporarily mute by a sudden attack of encephalitis. Unable to speak, unable to work, he passed the long days of convalescence playing Canfield solitaire. And he asked himself a simple-looking question: what are the chances that any given deal comes out successfully? The exact answer is combinatorially ferocious. 52 factorial starting positions, branching decisions at every move, a number so large no mathematician in history had cracked it by pen and paper. So Ulam did something radical, something slightly embarrassing for a theoretical mathematician. He decided that instead of computing the probability, he would simply simulate it. Deal many hands, count the wins, and the ratio would approach the truth. He shared the idea with his friend John von Neumann, who recognized its explosive potential almost instantly. On March 11, 1947, von Neumann wrote a handwritten letter to Robert Richtmyer at Los Alamos, proposing a step-by-step pseudocode for the first-ever simulation algorithm for an electronic computer. 1 year later, ENIAC, the room-sized vacuum tube beast at the Ballistic Research Lab in Aberdeen, ran that code, and the first Monte Carlo computation in history became real. And in 1949, the method went public in the Journal of the American Statistical Association. For months, the method was a classified code name, until the physicist Nicholas Metropolis gave it a glamorous, deliberately vague name, Monte Carlo. Named, according to Metropolis himself, after Ulam's uncle, who had to borrow money from relatives every time he went to the casino. 70 years later, this same idea, just deal many hands, count the wins, prices options across every exchange on Wall Street, teaches AlphaGo to beat the world champion at Go, and underpins trillions of dollars in derivative valuations. Today, in the next 20 minutes, we're going to find out why. Welcome to Monte Carlo. Before we price a single option, let's solve a much simpler problem with nothing but random numbers. We're going to calculate pi. Here's a 2x2 square with a perfectly inscribed unit circle drawn inside it. The rule is simple. We throw darts at the square completely at random, uniformly distributed. If a dart lands inside the circle, color it green. If it falls outside the circle, color it red. Then we count how many hit the circle and see what fraction that is of the total. Now let's throw many, many more. Watch how the estimator behaves as the dart count climbs. The yellow curve on the right is our running estimate. The horizontal teal line is the true value of pi. See how the yellow curve wobbles wildly at the start, then settles closer and closer to the true answer, locking in at 3.144 after 500 darts, with zero calculus, zero knowledge of the formula for pi. Here is why it works. The area of the circle divided by the area of the square is exactly pi over 4. And because our darts are uniform, the probability that any single dart hits the circle equals that same area ratio, pi over 4. So multiply the hit fraction by 4, and the law of averages hands you pi. But there is a catch that changes everything. The standard error of Monte Carlo shrinks like 1 over the square root of n. 100 darts give us 1 decimal of pi. 10,000 darts give us 2 decimals. To reach 3 decimal places, you need 1,000,000. 100 times more darts buys you only 10 times less error, not 100. That is the square root tax that Monte Carlo charges. This same idea, just count, divide, multiply, is about to price a $1 trillion derivatives market. But first, why does any of this actually work? Let's find out. Why does this actually work? Why should throwing darts or averaging coin flips converge to the truth at all? The answer lives in 2 theorems that look bureaucratic on paper, but are doing every bit of the heavy lifting behind the scenes. Theorem 1, the law of large numbers. Here are 8 independent sequences of fair coin flips, each running its own average from scratch. At first, every sequence wanders, but watch them lock onto the truth. Kolmogorov proved this in 1933. Either sample average converges almost surely to the true mean. That is the convergence guarantee behind every Monte Carlo estimator ever written. Theorem 2, the central limit theorem. While the law of large numbers guarantees we eventually converge, the central limit theorem tells us how fast. The standard error is sigma over root n e sigma, the spread of one sample, divided by root n, the number of samples averaged, which means 95% of the time the truth lies within 1.96 sigma over root n, of our estimate. Here is that band drawn on the running averages, and arrowing like 1 over root n, squeezing the bundle towards the truth. Now here is the truly strange part, the part that makes Monte Carlo indispensable in finance. On a log-log plot of error against the number of samples, Monte Carlo is the gold line S-slope minus 1/2, the same in every dimension, no matter what. Traditional grid methods like Simpson's rule look unbeatable at low dimensions, but their slope is minus 4 over d. As d grows, their lines flatten out. At dimension 9, Monte Carlo takes over the lead and never looks back. And in finance, dimensions explode fast. A portfolio with 100 assets? That's d equals 100. To hit 1% error, a grid-based method needs 10 to the 50th points and more than anything we could ever compute. Monte Carlo still needs just 10,000. Remember that square root rate. Next, we use it on real money. A stock price doesn't follow a formula. It follows a dice roll every millisecond. In episode 1, we derived the stochastic differential equation that captures that randomness, geometric-Brownian-motion. But for option pricing, there's one critical change. The drift is not the physical return mu, it's the risk-free rate R. That switch puts us under the risk-neutral measure Q, which is the only measure where this pricing formula from episode 2 is actually valid. How do we actually simulate this equation on a computer? We solve it exactly. Each step of the stock price is the previous price, times an exponential of a drift term, plus a random kick. But here is the single most important detail in all of option pricing. Not just R times delta t, it's R minus sigma squared over 2 times delta t. That minus sigma squared over 2 is the Ito correction. Without it, the math silently breaks, and you price options 4 to 5% too high. Now let's see it run. Here is one stock price starting at $100, evolving over 1 year, 252 trading days of random kicks, one possible future. Now watch 1,000 of them. Pre-computed, sorted by terminal price, and painted blue for the losers, red for the winners. Every single one of these is a valid continuation of the same initial stock, everyone consistent with the same geometric-Brownian motion. And here on the right, the distribution of where they all ended up. A beautiful, slightly skewed log-normal curve. Let's do a sanity check. The yellow line is the theoretical mean, S0 times e to the RT, which is $105.13. Under the risk-neutral measure, the discounted price has to be a martingale, and our simulated mean hits that theoretical line exactly. The Ito correction is doing its job, but notice, the teal line is the median at $103.05, mean above median. That $2 gap is the fingerprint of log-normal right skew. A few spectacular winners drag the average up, while most paths finish quietly below it. But here's the thing, we don't actually want the paths. We want the payoffs, average them, discount them, and we have an option price. Let's turn those paths into a price. For a European call option struck at $100, the payoff is simple. The greater of the terminal price minus the strike, or 0. The strike K is 100, our break-even. To the right of it, every dollar the stock finishes above 100 is a dollar of payoff. To the left, nothing. The option expires worthless. Now here is the distribution of where our 1,000 paths ended up. Painted green if they finished above the strike, in the money. Gray if they landed at or below, out of the money, contributing 0. 555 paths ended in profit. 445 delivered nothing. Now the crucial step. We average all 1,000 payoffs together. The zeros pull the average down. The big wins pull it up. Then we discount back to today at the risk-free rate, multiplying by e to the minus RT. That is our Monte Carlo option price estimator. Now let's actually watch it converge. On this plot, n is the number of simulations, 1 to 1,000. The yellow horizontal line is the true Black-Scholes price of $10.45. Our goal is for our estimator to find that line. Let's run it. The pink band is the 95% confidence interval, plus or minus 1.96 times the sample standard error. Watch it narrow like 1 over root n, squeezing the estimate towards the true price. And it lands, $10.46 after 1,000 simulated futures. Let's take a moment to appreciate this. Here is our Monte Carlo price, $10.46, found by rolling 1,000 dice and averaging. And here's the same option's Black-Scholes price, $10.45, found by solving a partial differential equation in episode 2. Two completely different methods, identical price. One walks forward through 1,000 random futures, the other walks backward through a binomial tree, and they agree to the penny. But there was a small problem on that convergence plot. 1,000 simulations was still off by about a penny. To cut that error in half, you need 4 times more simulations. Is there a smarter way? So, is there a smarter way? Here is the uncomfortable truth about plain Monte Carlo. The error of the estimate never goes to zero quickly. It shrinks like 1 over root n. That is its fundamental convergence rate. Doubling the simulations buys you only a 41% improvement, not 50, and it gets worse from there. Think about what this means in practice. If your first run gave you a price that's off by 1 cent, to have that error down to half a cent, you need 4 times the simulations. To cut it by 10, 100 times more. To cut it by 100, 10,000 times more. The square root is a brutal tax on randomness, and it only gets worse as you chase accuracy. But there is a clever trick, a free variance reduction, courtesy of symmetry. The normal distribution is symmetric around 0. Every time we draw a sample z, we can also use its mirror minus z for free. Each pair is perfectly anti-correlated by construction. When one goes up, the other goes down. Our new estimator averages the function at z and at minus z, and the variance per pair gains a factor of 1 plus RO, which, whenever RO is negative, beats plain Monte Carlo for free. Let's see it in action. 2 Monte Carlo runs, same 1,000 sample budget, plain on the left, antithetic on the right. Both should converge to $10.45. Here is plain Monte Carlo, jittery, noisy, wandering up to $10 off course. And here is antithetic, much smoother, hugging the true price from the very beginning. The standard error drops from 47 cents down to 33 cents. That is a 2 times variance reduction for free. For an at-the-money call, antithetic gives us 2 to 4 times. For deep out-of-the-money calls, up to 10 times. But watch out, antithetic only helps for monotone payoffs like plain calls and puts, and we can do even better. Next, control variates. We said we could do better, and we can, a lot better. The idea is simple. Find a quantity related to your payoff, but whose exact mean you already know analytically. Then subtract out the randomness it shares with the payoff. What's left has less variance than the payoff alone. That's the control variate estimator. Here's the trick in action for our call option. Each dot is 1 Monte Carlo sample. Terminal stock on the horizontal axis, discounted payoff on the vertical. Notice the strong linear correlation, 92%. The best fit line has slope 0.673. That is beta star, the covariance of payoff and stock over the variance of the stock. Subtract beta star times the stock residual, and the remaining variance shrinks by 1 minus rho squared. For our at-the-money call, almost 7 times less variance, for free. Now, a trick that saves you from wasting simulation time. Consider a deep out-of-the-money call struck at $150. Only about 3% of your simulated paths finish above the strike. 97% of the computation is silent noise. Important sampling fixes this. We tilt the sampling density to the right so most samples land where the payoff is actually non-zero. Then correct for the bias by multiplying each sample by the likelihood ratio, natural density divided by tilted density. In theory, the perfect tilt is proportional to payoff times natural density. Put them all together, and this is our variance reduction toolkit. Antithetic gives you 2 to 4 times. Control variates, around 7 times for at-the-money calls, more than 20 times for in-the-money calls. Important sampling, 50 times or more for deep out-of-the-money options where plain Monte Carlo almost gives up. 50 times fewer simulations for the same precision. That is the whole game. And everything we've built so far, averages, confidence bands, variance reduction, doesn't just live in finance. One estimator, 5 very different worlds. Everything we built today, averages, confidence bands, variance reduction, all distills into one tiny formula, the sample mean, and it is the closest thing to a universal solvent in all of applied math. In finance, it prices an option. Average the discounted payoffs over 1,000 simulated futures. In Go, it defeated Lee Sedol. AlphaGo's Monte Carlo tree search averages the outcomes of thousands of random rollouts from each candidate move. In Bayesian inference, Markov chain Monte Carlo draws samples from the posterior and averages over them. the heart of STAN, PYMC, and NumPyro. In quantum chemistry, variational Monte Carlo averages the local energy over electron configurations drawn from psi squared. The same idea powers modern neural wave functions. In reinforcement learning, the value of a state is the average return across sampled episodes. AlphaGo's tree search is literally this. 5 fields, 5 problems no human could integrate by hand, 1 estimator. Next time, we use Monte Carlo for the thing it was born to do, estimating the tail of a lost distribution, value at risk and conditional VR. Same math, different world.